This segment is about a special programming technique called recursion. We've seen already in the segment on stepwise refinements that one procedure may call another procedure. For instance, procedure 1 over here starts with blah blah, and then in the second statement it calls procedure 2. So what happens is that procedure 1 is suspended and that we now start executing procedure 2. So statement 1, statement 2, statement 3, and then when procedure 2 is finished, procedure 1 resumes. So we left off here at this statement, so we continue then this statement. And instead of calling another procedure, a procedure may also call itself. In that case, we speak of a recursive procedure. And that sounds like a bad idea. If one procedure keeps calling itself, then you may think the result will be an infinite loop. But if you do it properly, then you will not get an infinite loop, but you will get a nice result. And the algorithm may be much more elegant than if you do not use recursion. So that's the reason for using recursion. You get more elegant solutions. Before I show an example of a recursive algorithm, I will first show a recursive function in mathematics. And the most famous one is the Fibonacci function, which generates the Fibonacci numbers. And here you can see the first few Fibonacci numbers. And as you may see, each number equals the sum of the previous two numbers. So 3 equals 1 plus 2. And 13 equals 5 plus 8. And of course, we have a problem with the first few numbers because they do not have two predecessors. So what we start off by taking the numbers 0 and 1. And this is formalized in this definition here, the Fibonacci function. The Fibonacci function takes as number which Fibonacci number you want to compute, the number of the Fibonacci number in the range of Fibonacci numbers, and then the result is the Fibonacci number. So you can see here, if we're looking for number 0, then the result is 0. So that's this case. If n is 1, then the result is 1. So that's this case. And in all other cases, so if n is greater than 1, we take the sum of Fibonacci number n minus 1 and Fibonacci number n minus 2. So you see that in the definition of f, we use f. So this is the recursive part. We have two recursions here because we use the function f 2 times in its own definition. So these are called the recursive recursions, and there's one case where we use recursion, so one recursive case, and there are two cases where we do not use recursion. We call these the base cases. And as you see, we have two base cases and one recursive case. And for other applications this may be different, but you will always have at least one base case and one recursive case. So let's see what happens if we want to calculate f4. f4, well, n means n is 4. We get to this case, n is greater than 1. f4 equals f4 min 1 is 3 plus f4 minus 2 is 2, so we get F2. So F4 equals F3 plus F2. Okay, but what is F3? F3, again, we use the definition of F. So F3 is F2 plus F1. The next question, of course, is what is F2? Well, F2 is F1 plus F0. But F1 is our base case. N is 1, yields 1, and F0 yields 0. So we get 1 plus 0 is 1. So F2 is 1. So this recursion has finished, F2, and now we can continue with F3 because we were not yet finished with F3. We had suspended F3 in order to calculate F2. Now we can continue here because F2 is 1 and F1 is of course 1. So we get 1 plus 1 is 2. And now we can also continue with this call F4 because now we know the answer to F3. That is 2 plus F2. We also already have an answer to that one. F2 is 1. So we get 2 plus 1 is 3. So F4 is 3. Now let's have a look at how we can translate this Fibonacci function to pseudocode, to a procedure in pseudocodes. And it's almost the same. I've called the procedure Fibo. It takes one parameter, n, and I've changed, as you see, I've changed the base case a little bit. So first I had two base cases. For n is 0, we have as a result 0, and for n is 1, we have result 1. So we can also take that together and return n. With return, I mean that the procedure stops and it gives what is written behind return, in this case n, back as results to the procedure that called this procedure. So the results of calling Fibo with 0 or 1 is 0 or 1 respectively. So if that's not the case, we continue if n is greater than 1, and then here we have the recursive call to n minus 1, and the second recursive call to with n minus 2 as parameter. We sum them, and the sum is put in the variable result, and that's what we return. So the result of calling Fibo with parameter n is the sum of calling this procedure with n minus 1 and n minus 2 as parameters. And was it necessary to use recursion? Not in this case. Fibonacci can also be easily programmed using a loop. In this case, I use a for loop, which I didn't explain yet. We've already seen the for each loop, which is repeated, for instance, for each item in a list. In this case, we use a for loop, which is executed a special number of times. And it introduces a variable, and the variable gets incremented each time the loop is executed. So here we have a variable I, and first it gets the value 2, then the body is executed, then I is incremented, so I now becomes 3, and the body is executed until I is n, and then the body is executed one more time, and then the for loop finishes. And that's what we use here. what we do is we keep track of fn minus 2 and fn minus 1. I made these variables here to keep track of them. And of course they are initialized to 0 and 1. And then we keep calculating the next Fibonacci number until we have calculated the nth Fibonacci number. And of course the next Fibonacci number is the sum of the two previous Fibonacci numbers. And now we have a new previous Fibonacci number, which is the old previous Fibonacci number. And we have a new previous Fibonacci number, which is the current Fibonacci number. And then we can repeat until we have calculated the nth Fibonacci number, and that is the result that we return. And this whole part works only if n is at least 2. So if n is smaller, we need to make sure it's not executed. So in the beginning I check if n is 0 or n is 1. In that case we can stop and return 0 or 1 respectively. Now I get to the most famous problem that is used with recursion. That's called the Towers of Hanoi. And it's a game which is played with a number of rings, which can be placed on top of each other, and they all have different sizes, and 3 poles. And here you can see 4 rings and 3 poles. And the goal of the game is to move all rings from one pole to another pole. There are 2 rules. Rule number 1. You can only move 1 ring at a time, and the second rule states that you can only place that no ring may be placed on a smaller ring. So this configuration is okay, but we cannot place, for instance, ring 2 on top of ring 1. So this is a diagram of the Towers of Hanoi, and I will now give you a demonstration, not with rings, but with buckets. So our goal is to move this tower of 4 from this position to this position. Of course, it's not allowed. We can only move 1 ring at a time. So we have to make the problem smaller. We have to reduce our problem in such a way that eventually we will come to the base case, and the base case in this case is of course moving 1 ring. How can we split up our problem in such a way that we have an easier problem that's closer to the base case? Well, we can split our tower in such a way that we have the bottom ring and all the other rings. And if we make this, we split up our problem in this way, then it becomes very easy to solve this in a recursive way. So that means that we need a procedure to move n rings from position A to position B. And then it's very easy. If we have such a procedure, then we move 3 rings from position 1 to position 2. We move 1 ring from position 1 to position 3. Moving 1 ring is trivial. And then again by recursion we move 3 rings from position 2 to position 3. Let's rewind. How do we move these 3 from here to here? Well, again, it's a recursive call. How do you move this tower of 3? We will first move this tower of 2. So that's moving 2 rings from position 1 to position 3. moving one ring from position 1 to position 2. That's the base case, and then we have to move these two from position 3 to position 2. How can we do that? By moving one ring to here, it's trivial. One moving to here, trivial, and moving one ring to here, that's also trivial base case. And now you see, now we have managed to move 3 rings from here to here. We can make this move, and now we need to make the move from these 3, position 2 to position 3. To do so, we need to move this one to this position, and so we need these two out of the way. So that will be like this, this, this. Now we can move this one here and these two here. Of course, we need to split up that. It's also a recursive call. So it goes here, and goes here, and we're finished. So you see, we have defined our procedure in such a way that our problem is reduced to a smaller problem that has the same structure and that is a little bit closer to the base case. And the base case here is moving one ring.